Welcome everyone. Thanks for joining us today for the multi-cloud talk. My name is Chirag Narang. I'm a product manager at Yugabyte. Today's talk will explore key considerations for designing and operating multi-cloud database strategies, and I'll demonstrate how companies can use Yugabyte Platform as a springboard for innovating with multi-cloud. So let's talk a little bit about what we are going to go over. First, we'll look at the different cloud models, and then why businesses are leaning more towards multi-cloud. After that, we'll go over different architectures and then discuss database deployment challenges. In the end, we'll have a live demo of Yugabyte Platform, and finally, some time for Q&A. There are typically 4 different cloud models. The private cloud model is about leveraging cloud resources within a private environment. This model is particularly useful for industries that are heavily regulated and companies that work with sensitive data. The public cloud model is about leveraging public cloud providers like AWS, Microsoft, or GCP. This model is used for scalability and initial cost savings. It's a highly attractive model with capital-strapped institutions looking to quickly get up and running with their businesses. The next one is a hybrid model. Hybrid model combines public cloud computing with a private cloud on-premises infrastructure. This approach is best for companies with dynamic or unpredictable computing needs that require direct control over their environments to meet security, business governance, or regulatory compliance requirements. The last one is a multi-cloud. Multi-cloud is a strategy that utilizes the cloud infrastructure of 2 or more public cloud providers. For example, AWS and GCP. Company may find it beneficial for both business and technical reasons to rely on multiple cloud vendors instead of locking in with a single provider. For example, a company may decide to use one provider for its data services, another one for serverless, and yet another one for user authentication. This model is gaining a lot more traction in the market these days. As per Gartner, nearly 81% of all public cloud users are already using this model. So why more and more organizations are leaning towards multi-cloud architectures? These are some of the benefits that you get once you start onboarding multi-cloud architecture. Avoiding vendor lock-in. AWS has clearly won the hearts of developers. But those early decisions to standardize on AWS are now being revisited. With Azure and GCP offering similar services at a competitive price point, enterprises are looking to reduce their over-reliance on AWS. Improve resiliency. Cloud outages are inevitable. All of us remember the day internet died when S3 went down. Multi-cloud architectures can help you with an added layer of protection against security threats and outages. If one cloud is unavailable, the other clouds can remain online, enabling you to continue servicing your users. Tapping into new markets. Multi-cloud can help you to tap into new markets by taking advantage of regional data centers. Utilizing latest hardware for performance improvements. Cloud providers offer a wide range of virtual machines based on the latest hardware for a variety of specialized workloads. And you can also use best of breed services from their portfolio. For example, GCP has a strong play for data scientists. Azure tends to appeal to traditional Exchange, Outlook users, and AWS is known for its compute portfolio. Next thing is achieving compliance with a single system. Regulations such as GDPR in the EU can often be a driving force for companies with global user bases to adopt multi-clouds. If your primary cloud provider does not support all the regions where your customers' data reside, you might want to consider a multi-cloud strategy. And the last one is performance. You can optimized for performance at the best possible price. These days, you can get a good price by combining Azure's low priority virtual machines or AWS spot instances and GCP's preemptible VMs. Now next, let's see different multi-cloud architectures which can unlock these benefits. First one is an enterprise architecture. In this architecture type, each solution is still deployed in its entirety of a single platform. For example, an organization could run its CRM as a SaaS application on Salesforce cloud infrastructure, its e-commerce on AWS, and its ERP services on Microsoft. Still, none of these systems span multiple cloud platforms. Each application is siloed within a specific cloud. In a solution architecture, the application crosses multiple cloud boundaries. For example, you might use Google Spanner as a database, Azure Active Directory for user management, while using AWS EC2 instances for all for a single application. This type of architecture really allows you to mix and match best-of-breed services from different clouds. Data architecture. In data architectures, workloads are deployed on more than one cloud based on the location of the data. This is done primarily to achieve regulatory compliance. For example, you could use Google Spanner to store US user information and Azure Cosmos DB for European users. And the last one is a cluster architecture. This architecture is unique to databases. It requires different nodes of the same cluster to be deployed in multiple cloud environments. It's the same cluster, different nodes in different clouds. It extends the geographic reach of your applications by synchronously replicating data across cloud providers. For example, a 3-node database is distributed in AWS, GCP, and Azure regions. In today's demo, we'll be focusing on this architecture. As easy this may sound, implementing these practices can be extremely difficult. Without careful planning, architecture review, and execution, multi-cloud architectures can lead to greater complexity, cost, and effort than single cloud architectures. When it comes to adopting multi-cloud databases, most companies are facing similar challenges. Over and over, we hear the same set of questions. For my transaction apps, what is the right data architecture? How do I scale horizontally and still maintain data integrity? How do I manage applications across the clouds while maintaining security? How do I give the operators the tools to offer a database as a service without spending all their time managing the database? I know I just touched on a few, but ultimately it comes down to ensuring that developers can access the rich database feature set they are familiar with and having the database optimized for multi-cloud use cases. So let's move on to the demo. In today's demo, I'll show you a true multi-cloud architecture that we talked about using Yugabyte Platform. Yugabyte Platform is a management platform for building your private database as a service. It provides a console that eases the process of deploying and managing Yugabyte cluster across public and private clouds, including Kubernetes. It also offers day 2 automation capabilities like rolling upgrades, data backup, data restore, inbuilt monitoring with Prometheus, and automated health checks. In today's demo, I'll show you 5 things. First one is global distribution. Cluster will be located everywhere. This cluster will be globally distributed in a matter of few minutes, not hours, not days. And let me clear this. This is going to be a single database across 3 different geographies, not 3 different databases. And we won't need to set up any out-of-band replications for this to work. Second, there'll be no maintenance window. This is not like our legacy databases. It has to be available 24/7, and it has to be fully fault tolerant to any cloud outages. Third, data security. Security is paramount these days. So our database has to be secured from day one. Fourth, I'll scale the cluster horizontally without compromising data integrity and ongoing transactions. And last, all this will be dead easy. Everything will be managed from a single pane of glass without introducing multiple tools into the mix. This is my cluster spec. I'll be using AWS, GCP, and Azure. In total, there'll be 9 nodes, 3 nodes in each data center. I have selected North Virginia, LA, and London as my data centers. As I mentioned, there'll be no out-of-band replication. We'll use default synchronous replication. For security, I'll be securing data with encryption and transit and at rest. And there'll be hourly backups in AWS S3. With that, let's start the demo. I'll log into the platform. And then the next step is to create a cloud provider. You can choose from AWS, GCP, Azure, or Kubernetes, but I'll use the on-prem cloud provider because it gives me the most deployment flexibility. I need to provide details on my SSH user, which will be used for provisioning and lifecycle of my database nodes. Here goes my SSH user, and I need to provide my SSH key. And for the rest of config, we'll just go with the default settings. Next step is my instance type configuration, like number of cores, memory, mount point for storing my actual data. And then we'll go ahead to configure regions and zones. For AWS, I'm going to select Virginia and US East, Azure in London, and GCP in LA. And then finally, I'll add GCP in LA. Right, with that, let's move on to adding cloud instances. So to save some time, I've already spun up my VMs and cloud providers. So I'm just going to add those IPs here. So first I'll select my zone, choose my instance type, and add an IP address. Copy my IP address and give it an instance ID. For the purpose of this demo, I'll add few IPs manually, but rest of them I have already scripted using an API call, so I'll do it behind the scene. It will save us some time. Yeah, here I'll refresh the page and see all the instances. As you can see, all 9 nodes have been provisioned. Let's move on to our backup strategy. Here I'm going to create a backup in Amazon S3. I'll be adding the details of AWS access key and secret, which is really easy to create in AWS, and provide details on my S3 bucket where backup should be saved. Once that's done, I'm going to save this config. Now backup is done. Let's move on to data security. First is data address. I'm going to use my AWS KMS for the key management. I'll need to provide AWS API key and access key ID and KMS key ID, and also the region where this KMS key is created. US West 2, and we'll save this config. Next is encryption and transit. You have an option of bringing your own CA authorized cert from Venafi, DigiCert, but for the purpose of this demo, I'm just going to use a self-signed cert. So with that, now let's just go ahead and deploy our cluster. I'll choose my cloud provider which was created, regions, and increase the number of counts and different AZs that were configured during the cloud provider configuration. Bump up the total number of nodes to 9, 3 in each data center, and add few more controls for data security. Enable node-to-node TLS, client-to-node TLS, and encryption at rest for our data. I'll select the KMS config. With that, we are ready to create our cluster. Soon, cluster will be in ready status. Let's just refresh the page to see if it's there. Right, everything looks good. Let's go to the overview page. Here we can see the cluster is distributed in 3 different geographies as we had configured. Let's close this and check the node status. I can see all 9 of my nodes are live and healthy, so it means my cluster is fully up and running. So everything looks good. But remember, our cluster is empty at the moment. There is no data. So next step for us is push some sample data through a load generator. I'm planning to use SQL load generator. So I'll go to the more tab and pick a sample app from here. It gives me all the IP addresses of 9 nodes. So we are connecting to those nodes directly. Let's take that and go to our terminal and run that sample load. It will take a few moments for this data to be loaded, and once data starts loading, we'll go and check number of operations per second for this sample load. Right, let's wait and now check for the number of metrics. Number of operations per second. All right, looks like our ops is settling down, and it should reach its peak soon. All right, as we can see, it's just trending around 800 reads per second and 500 writes per second. So that was relatively easy, right, for us to deploy a geo-distributed multi-cloud cluster across the globe, which is secure from day one. And I was able to manage my day 2 administration tasks as well. So let's move on to our next objective, which is horizontal scalability. I'll be scaling from 9 nodes to 12 nodes, which means now I'll have 4 nodes in each data center. The first step here is we have to increase our node pool by adding 3 new instances from the cloud config page. I already have those IP addresses available, so I'll just add 1 node to each data center. Select US West 2, instance type, and then IP address. Do the same thing for London and Virginia. Now with that, our nodes are available. Let's edit our cluster to scale up. It's as easy as increasing the node count in each data center. So we have done that. Let's save this configuration, and our cluster should be ready shortly with the added new capacity. So now I want to test the cluster output, but remember I've added new nodes, so I have to include them in my client testing. So I'll stop my sample tests in the background and then include these new IPs in my sample load testing. Here I'll grab the IPs. As I shut down the test, you'll see the ops have dropped to 0 as expected, and on our next run, I expect ops per second to increase this time because I have added more capacity to my cluster. So here you can see ops per second have dropped to 0. Let's rerun our test. It will take a few seconds for data to be loaded in the cluster. Let's refresh the number of ops per second. Okay, it's trending up. Let's wait for a few more moments and then check again. Yeah, as you can see now, data is growing. Number of ops have increased from 800 to almost 1300. So you can see now total throughput through my cluster has increased as compared to the original configuration where we started. So with few clicks, I was just able to scale the cluster on demand. With scalability tested, now let's move to our data backup strategy. For my data backup, I've selected S3, so I'll just create a scheduled backup using a cron expression to take full hourly backups of my entire namespace. You don't need to take any manual backups. Now with this, you can restore your data at any point in the same cluster or in any other cluster running anywhere else. Now let's move on to our next objective of fault tolerance. As we talked about cloud outages, which are inevitable, right? So we want to check our cluster for fault tolerance to cloud level failures. I'll simulate outage by bringing down the entire data center in AWS. So I'll be down from 12 to 8 nodes. With this outage, I want to verify the impact on client application. So let's navigate to the AWS console. And I want to stop all the nodes running inside AWS. Here we are in AWS. Select those 4 nodes and change the instance state to stop. Okay, now instances are stopped. Let's verify the node status in our cluster page. Soon we should be seeing the nodes will be unreachable. Let's refresh the page and see. Okay, so all my nodes are unreachable now. And we want to verify the impact on our client application, which is, by the way, still running in the background. So let's just check the total ops per second. How is our client app affected with this cloud outage? We'll wait a bit for ops to settle down. It can take some time for client application to recognize that database nodes are not available. So we are seeing a trend. Number of ops have dropped from 1300, it's coming down. Let's wait a little bit longer. Remember, now we are running at a reduced capacity. We are down from 12 nodes to 8 nodes. And you can see that number of ops have gone down to our original cluster configuration of 9 nodes. My client application still continues to work as expected. And the loss in ops is because our cluster has been scaled down. But still, the database continues to serve the client request, and it abstracted from any cloud failures. At this point, you can easily replace those AWS faulty nodes with nodes in other regions or scale up the nodes in a different cloud provider. We saw today how easy it was to scale an existing cluster. That will give you the same throughput that you were seeing before the outage. So you saw how easy it was to create a geo-distributed, multi-cloud, fault-tolerant database using Yugabyte Platform. That's it in terms of the demo. I hope you enjoyed it. So to recap what we saw today. With the Yugabyte Platform, I was able to build a cloud-agnostic private database as a service. The Yugabyte Platform allows you to deploy across all major cloud providers, private data centers, and Kubernetes. You can spread your data across AZs, regions, or even cloud providers. YugabyteDB can survive multiple failures. We saw in the demo, it survived the entire data center failure. I was able to horizontally scale my deployment without any application downtime or application re-architecture. With a single pane of glass, I was able to manage from day one deployments to all my day two operations. And enforcing security was easy as point, click, and deploy. And the last one, YugabyteDB is fully open source under Apache 2.0 open source license. Thank you.